Hello students, so in this video we are going to cover name reactions from chapter 12. So this chapter is aldehydes, ketones and carboxylic acid. So we have a lot of name reactions and it's a very important chapter too. So let's see what are the name reactions under this. So the first one is Rosenmund reaction. Rosenmund reduction. So as the name says, it is a reduction reaction. Basically, you're trying to add hydrogen. So let's see how the reaction proceeds. For this, we need acyl chloride. This is your acyl group and this is the chloride. So acyl chloride with hydrogen in the presence of, whenever we have hydrogen, we always will add palladium. BaSO4 is like a poison, which means you want to limit your reaction to a particular functional group. If you don't add this, the reaction will move forward to another functional group. So basically it will stop, it will control the reaction. So here what happens is, you have a hydrogen molecule. Now one hydrogen atom goes to Cl to form HCl. What about the other hydrogen atom? That is going to be replaced in place of Cl. So RCOO, RC double bond O is here. Instead of a Cl, second hydrogen atom will be placed. So this is a special method of preparation of only an aldehyde. Because you can't have an R group over here because you're trying to add a hydrogen. And one side of the carbonyl group has to be a hydrogen, and that is possible only when you prepare aldehyde. So let's see an example for the same reaction. So here I have, instead of R group, I am taking CH3. The remaining will all be the same with palladium and BaSO4, barium sulfate. Now what will happen here is hydrogen will pick up a chlorine to form HCl, that remains the same. Instead of the Cl, you have the second hydrogen atom that will sit here. So your product here is going to be CH3, C double bond OH. So you're trying to form acetaldehyde or ethanal as your product in this case. Now instead of R group, they can give you CH3, you can get C2H5, you can get C6H5. They're all the same. Basic function of these are the same. Now why is palladium added? Hydrogen is a gas. For its activity, it needs a surface. That is being provided by palladium. You've learned this in grade 11 also. How do you store hydrogen or how the hydrogen activities increase? Basically in the presence of platinum or palladium or a nickel as a catalyst. Barium sulfate is added so that further reaction doesn't take place. It is a poison in the reaction. Let's move to the second set of reaction, which is Stefan's reaction. Now, in Stefan's reaction, your starting material is a nitrile with the C triple bond N. Now, here also you are trying to add a hydrogen. So, you are adding hydrogen, but you have other set of reagents. This will happen in the presence of acid and stannous chloride also. These are in the presence of these reagents, your entire reduction is going to take place. So you have two hydrogen atoms here. One hydrogen atom will go to carbon, the other hydrogen atom goes to nitrogen, breaking the triple bond in the center. One bond will break. So the R group will remain the same. One hydrogen goes here, one hydrogen goes to the other nitrogen. Instead of having a triple bond, you will have a double bond. Now this will undergo hydrolysis. You want to prepare an aldehyde, right? So you have to undergo hydrolysis to this same reaction. So I'm just copying down this product over here. N, H and the H plus hydrolysis will take place. Now let's see how the hydrolysis takes place. But for hydrolysis, you need a catalyst, as it's an acid catalyzed reaction. So in this case, what will happen is oxygen will sit in place of nitrogen. Here, this entire one, NH, will pick up both the hydrogens and will form ammonia. This NH will pick up two hydrogens and form ammonia. This one oxygen will be double bonded to carbon. So this remains the same. Double bond, wherever NH was there, oxygen is going to sit there. You can prepare aldehyde only by this method. Ketone cannot be prepared because this carbon is going to have a hydrogen attached, and that carbon is going to be the aldehyde carbon in the end. So this is going to be Stefan's reduction reaction. So both of these are reductions. Now the next one is Aldehydes reaction. So let's see how the reaction proceeds. The third one is Aldehydes reaction. Now under this reaction, first let's see the single step reaction, and I'll tell you how that product is forming. So here we have toluene first as your reactant. So I have toluene. This is an oxidation reaction. So I'll have oxygen. I have a set of reagents here. I have chromyl chloride, CrO2Cl2, and I have CCl4. And the CH3 is now going to change to an aldehyde group with release of water molecule. Now with one step, it's difficult for you to tell how this methyl group is changing to an aldehyde group here. So there's a small step where I will explain this, showing the entire process. So here I will show you from where this methyl reacting with chromyl chloride. So I have the methyl group reacting with chromyl chloride. CCl3 is a solvent here, a medium for it to react. Now what will happen is I'm going to take two of this molecule. Alright, so here from the toluene methyl group, one CH hydrogen is retained. The other two hydrogens are coming out. But in place of that, this entire group is going to sit. So here I will have bonded to carbon, one chromyl group, oxygen, I have C, two chlorine atoms, another oxygen here will become OH. So whatever hydrogen is left out here, one hydrogen will go to the OH. Now this is the entire chromyl group. I have one Cr here, two oxygens here, two Cl atoms here. This hydrogen is coming from this group. Similarly, one more group will form in the same way. Oxygen, Cr, OH, Cl, Cl. So it's a whole big complex that is forming. A chromyl chloride complex is formed with toluene. So because I have two Cr groups here, I am taking two of this. Now to this I am going to add water molecule. Alright, so when I add water molecule, Here in this case, hydrogens from here is picked up by this oxygen. These oxygen have lone pairs alone. So this oxygen picks up a hydrogen, this oxygen picks up a hydrogen, and the bond is going to break. So basically I need two water molecules. So here this bond is going to break here. So I'll put a dotted line here to show the bond breakage. So I'll have the benzene ring with a CH, oxygen picking up a hydrogen from this water molecule, oxygen again picking up a hydrogen from the second water molecule. What happens to this entire complex? So I have Cr with an OH, 2Cl, and this, there's another bonding here to chlorine. The remaining part of each OH molecule will be bonded here. So I'll end up getting two of this. So here from water, hydrogen from each molecule is picked up by these oxygen atom. Each water molecule is having the OH part. That OH will go to chromium here to form the second OH. So that way I'm getting two molecules here. Now what will happen to these? Here from this water molecule is released out. OH and one hydrogen from here will pick up, will move out as water molecule, and here I will get a double bond oxygen. So I will get benzaldehyde. Now to this again water molecule is released out for the other product. In the same way, OH from here and a hydrogen from here will release out, and you will end up getting a double bond on this oxygen. So Cr double bond Cl, Cl. So these are going to be how the products are going to form in your Aldehydes reaction. This is your major product. So this is one step. In case you don't understand, you are confused as to how you're going to draw this, you can always refer to this one mechanism to see how the product is forming. So you'll have a rough idea of how this is there. But this mechanism is really not important for a state level board exam. You just have to know the overall reaction. That's all. This mechanism is not needed. Alright, so our fourth one is Gattermann Koch reaction. Gattermann Koch reaction is basically a preparation of benzaldehyde starting from benzene. So we have benzene plus carbon monoxide in the presence of HCl, and we have a Lewis acid here, anhydrous AlCl3. This basically helps in removing the chlorine from here. So to the benzene ring, what happens here is, for benzaldehyde you need a carbon, you need a hydrogen, you need an oxygen. So what's the purpose of a Lewis acid? Lewis acid will pick up the chlorine so that this hydrogen is free for bonding here. So I'll have CHO in this case. So you're trying to form a benzaldehyde from scratch. Now the next one is Clemenson's reduction. Clemenson's reduction. So let's see what all you need for this reaction. So here our starting material is going to be a ketone. Clemenson's reduction. To this, 4 hydrogen atoms. But what are our reagents? Zinc amalgam and concentrated HCl. These are our reagents for the entire reduction. Now here what we are going to do is, of the 4 hydrogen, two of them is going to remove this oxygen. So when the oxygen goes out, since you have double bond, it is going to be occupied by two hydrogens. So R, C, one hydrogen, and an R dash. So instead of a double bond oxygen, I have two hydrogens. But what about the other two hydrogens? That is going to be bonded with oxygen to form water molecule. So here it is a reduction of an aldehyde or a ketone to form a hydrocarbon. Now the same thing when I try to do with an aldehyde. Here, plus 4 hydrogens in the presence of the same reagents, zinc amalgam and concentrated HCl. Now when I do this, 2 hydrogens will replace the oxygen atoms. These were already there in the reactant. The remaining 2 hydrogens are here. 2 more hydrogens will pick up oxygen to form water molecule. So here you are trying to form it from an ketone and the second one from an aldehyde. Now the sixth one is Wolff-Kishner's reduction. Wolff-Kishner's reduction. Now in this case, you are going to take an aldehyde R, C double bond O, R dash. Now to this you are going to add hydrazine. NH2, NH2 is called hydrazine. Now when you do this, this double bond oxygen, this oxygen will go out with 2 hydrogens from here. So I'm going to form water. From one of the nitrogens, 2 hydrogen and this oxygen goes out. So instead of double bond O, it will be double bonded to this nitrogen. So here instead of double bond O, double bond to that nitrogen and the remaining will be the same. Now this is going to react with sodium hydroxide and ethylene glycol. So here I will have sodium hydroxide and ethylene glycol. When it reacts with sodium hydroxide, this entire part will come out. And you're going to get hydrogens are going to move here. 2 hydrogens from here will go to carbon. N2 gas will be released out. So R, instead of having a double bond there, it will be CH2 and N2 will come out as gas. So this is going to be the entire reaction using a ketone. The same reaction if I'm trying to do with respect to an aldehyde, it's going to be the same. So I'll take an aldehyde here, alright, and I'm going to use hydrazine. Now same thing, hydrogen from here and oxygen goes out as water molecule. The remaining part will be double bonded to carbon. Double bond N, NH2 plus water. Now this will further react with sodium hydroxide and ethylene glycol, and this is going to form, instead of having double bond N, 2 hydrogens from here will be bonded. So H2 plus N2 gas. So the difference between the first product and this product here is that you had 2 R groups, but here you have 1 R and 1 hydrogen. But this reaction can be written for both aldehyde as well as ketone. Now our next one is haloform reaction. So in the haloform reaction, I'm going to take a ketone. So here there's a specific one. You need to take a ketone which has at least one methyl group. That's important. So here I've taken a ketone. I'm trying to react this with halogen. 3 halogen atoms, 3 halogen molecule plus NaOH. Now when I have this, I'm going to form my product CH3. Instead of having this, I'm going to remove the entire group over here, retaining one hydrogen. So one hydrogen will be there. I'm retaining that. All other bonds will be replaced with this halogen. This is going to be your haloform, and that's a general formula. Carbon with a single hydrogen and 3 halogen atom is called as haloform. Now the remaining byproduct RC double bond O, and it's going to pick up this ONA from here. So NaO is done. The entire this group is also done. Now here you still have some amount of X molecules that is going to react with sodium halide plus water molecule. There's a mechanism to this, but for the state board level, we don't really have to write the mechanism. So if you know from where which product is being formed, you just have to go back and balance the entire equation for this. So our next one is aldol condensation. So for this, let's see a general equation, how to do this reaction. So here I am taking an aldehyde and I am taking another aldehyde also here, just to explain this in detail. Now this has to happen in the presence of dilute NaOH. Dilute NaOH. Now here what happens is, this carbon will get a negative charge when oxygen picks up this hydrogen. So the oxygen here is going to pick up this hydrogen. This double bond will break and this carbon will be bonded here. So let's write the entire structure. Starting from here, we have R group, CH2, this carbon with this hydrogen here. It's all the same. But here what happens is, this double bond will break and you have an oxygen here. This oxygen is going to pick up a hydrogen from this carbon. So it's going to become OH, and this carbon is going to be bonded directly to here after this hydrogen goes out. So you will have a CH, then the remaining part of the R group and CHO. So you have this as your product. Now this, when I try to heat it, what happens here is, this OH will pick up this hydrogen from here and eliminate water molecule, and a double bond is formed in between these two carbons. So I have RCH2, this carbon double bonded to the next one, and you have a CHO, and the remaining groups are the same. This is going to be the aldol condensation. Now this same thing, when I try to do another one called as cross aldol. Let's see an example. Cross aldol condensation. Now in cross aldol condensation, I'm going to take, say, an aldehyde, and I'm going to take another aldehyde here. Now this is going to happen here. Instead of taking CH3, I'm just taking CH3, CH2. Because it's a cross aldol, you need two different aldehydes. One is with 2 carbon chain here, the other one is 1 carbon. So basically this is propanol and this is ethanol. So I've taken two different aldehydes. Condition is going to be the same, dilute NaOH. The process is again going to be the same itself. There's no change in it. I'll write down the product here. CH3, CH2, C. This double bond will break. This oxygen is going to pick up this hydrogen from here. It will become OH. This carbon has a hydrogen. I'm putting that over here. This carbon will be bonded to this high carbon from the second one. And you get a CHO. Same as this product. Now the next one, what I'm going to do here is I'm going to heat this. So once I heat, I will have elimination of water molecule. So OH and this hydrogen, which is on the side of the aldehyde, will come out and you have a double bond here. So I have CH3, CH2, C, double bond, CH, CHO. So basically aldol is with respect to two same aldehydes or two same ketones. Cross aldol is when you have one aldehyde of a different chain and the other aldehyde of another chain, or an aldehyde and a ketone. That is going to be your cross aldol. Now let's see the next one, which is Cannizzaro reaction. Cannizzaro's reaction. Now, in the previous cases, we had an aldehyde which had an alpha carbon. The carbon that's next to the aldehyde group is the alpha carbon. What if you don't have an aldehyde that does not have an alpha carbon? Alpha hydrogen, sorry. Aldehyde group having carbon which has an hydrogen. That is alpha hydrogen. But if you don't have an alpha hydrogen, then what do? You do a Cannizzaro's reaction. So under Cannizzaro's reaction, I'm just taking two aldehydes in the presence of concentrated KOH or concentrated NaOH. This is in presence of dilute, this is going to be concentrated. Now because it doesn't have an alpha hydrogen on the R group here, this is going to form a salt of carboxylic acid plus the second compound of this will form an alcohol. So the first compound is going to form a salt, K with the salt. The other one is going to form a alcohol. So in this case, aldol and cross aldol is in the presence of dilute NaOH, whereas Cannizzaro is in the presence of concentrated KOH or concentrated NaOH. For both of this, you need alpha hydrogens. Basically, your hydrogens, you have an aldehyde group. Aldehyde will have an adjacent carbon which will have a hydrogen. That hydrogen is what is called as alpha hydrogen. Only because that alpha hydrogen is one that's going to be bonded to the oxygen here. That's why you need alpha hydrogens for aldehyde, for aldol and cross aldol. When you don't have both the alpha hydrogens for both of this, then you go ahead and do Cannizzaro's reaction. So I hope this video is helpful for you all. This has a lot of name reactions in this, so please go through this, and if you want any other videos, please don't hesitate to drop a comment in the comment box or to my email ID. Thank you so much for watching.